We last left off, we were about to do a line interval.
Yes.
You have that calculus?
I have.
Okay. Calc 1, 2, 3, 1. Okay. So we had an electric field that I was putting in the plane of the board. That is looking horrible, but we'll go with it. So that's my electric field. My magnetic field is perpendicular to that. I feel like I drew it better last time.
I think so.
And so on. So they are perpendicular to each other. I have the electric field going this way and the magnetic field going that way. Now, recognize that when light's coming at you, when an electromagnetic wave is coming at you, you have a lot of different electric fields that are all around. I mean, they're not all just one-dimensional like that.
Mhm.
You're being bombarded with 360 degrees of electric field, but each electric field is traveling in a plane. You just have a bunch of electric fields coming at you. And presumably, the hand gestures just really cinch the understanding,
Absolutely.
because that's the way I want it to look from my point of view. There we go.
Okay.
Now it's perfect.
Welcome in.
Hello, good morning.
Good morning. Isn't it crazy?
See if you can find a seat.
Where is everybody?
That's a good question.
They might all be getting coffee with us. I think we would.
That's super rude of them
I know.
to not invite
So-
us.
So this morning, I needed to take one of our dogs to the vet, drop him off. Forgot about it. My wife reminded me. And so I sort of rushed through the morning, get the dog on a leash. Other two dogs are going crazy. Open up the door. One of the other dogs escapes.
Oh no.
Out the front door. At this point, it's after 7:30.
Yeah.
I hop in the car, go. I knew the direction he ran in, and I just hope I would get lucky.
Yeah.
While I was out, he did come home. So I come home, and then ask my wife, "Are you in a position to actually take the dog to the vet?"
Yeah.
Which was not expected at that point, and so she does. So I'm rushing. I get here, and I could have taken the dog to the vet. It turns out.
Yeah, you could have.
Luis was here all the time, so this was for you.
You get the gold star today.
Yay! I love gold stars.
Glad you did it.
Oh, thanks. You took all the effort. You should have seen me trying to get out of my car in the parking lot. It was like, it's so low to the ground. I hate it.
All right, so we have the electric field, so I'm taking one electric field that's oscillating parallel to the board, and then the magnetic field is perpendicular to the board. My electric field, I am going to describe by the following equation. I have some amplitude. You can go cosine or sine, and even though I started it here, which makes me think sine, I'm still going to use cosine here. And then kx minus omega t. The magnetic field is some amplitude times the cosine of kx minus omega t. Since they're in sync with each other, they have maximum value at the same time. They are they're zero at the same time, and so forth. This part out here is the same for both. Kx minus omega t is the same for both. were gonna use Ampere's law to start with. So that's the wrong one. That should be a B. I have to use Ampere's law, Maxwell's law and Faraday-Lentz's law. Both, I traditionally start with one of the other, so my hesitation was I was trying to remember which one I'm supposed to start, what I usually start with. Alright, so B dot delta L is equal to U naught I plus U naught, nope. Yeah, no, that's right. U naught epsilon naught delta phi sub E over delta D. What did I start with the other one? No, I started the last time. What did I?
This one, the E, and then that. This is what I have in my notes.
A. So I started with Faraday-Lentz's and not.
Yeah.
Okay. Probably would have helped if I drawn up my hearing with. Earlier, there we go. So I'm looking at a range right here. So if we look at that bit, I have an electric field. So blue for electric field here. So I have an electric field value there, and then an electric right beside it, an electric field plus some change in the electric field. This distance here is delta x, and the height of this is h. Officially, delta x, when we're creating this pretend loop here, delta x is really small. Using calculus, infinitesimally small. The height, h, is completely arbitrary. I mean, height is a distance, E is not a distance, it's an electric field, and so they're not really using the same units, so h is just some arbitrary number, which fortunately will go away at some point. Since I am not doing this first, I'm doing this second, I'm going to hop to a new screen. And we're going to start out with Faraday-Lentz's law. So the sum of the electric field times the length is equal to negative change in the magnetic flux with respect to time. As we derived last time, this would be, I got a little A, B, C, and D. So what's it, A, B, C, and D? Does that match what I did last time in terms of labeling?
I think so. Yes.
And I am gonna go, oh, I forgot to draw in my magnetic field. In this region right here, my electric field's going this way, my magnetic field's coming out of the board, and so my magnetic field is coming out. So this is my electric field along A dot delta L plus the electric field along B dot little b dot delta L, that's A, B, plus the electric field along C dot delta L, C, plus the electric field along D dot delta L, D, equals, and we got as far last time as A over delta B over delta T, or negative A. There's the 13th. I assume you're still taking notes as opposed to doodling at this point.
Can you confirm or deny?
All right, so let's take a look at these dot products. The electric field is going up. D, this delta LA, it is a vector. I'm going around this loop here. So delta LA is a vector going from my starting point to here. I can start anywhere, but I'm starting in the lower left-hand corner. And so my electric field is going this way. Delta L sub A is going that way. What is the dot product? Two vectors that are perpendicular to each other.
0?
Yes. So that is 0, because my electric field along path A is perpendicular to delta L along path A. Matter of fact, which other dot product is going to be 0?
C.
Wait, say that again?
C.
I hear the E. I'm missing the C or the B.
C.
C. All right. Yes, that's also 0, because that's the electric field along C is perpendicular to delta L along C. If you're doing a dot product between two vectors going in the same direction, positive or negative?
Positive.
Indeed. Just a quick flashback. A dot B is equal to the magnitude of A, the magnitude of B, times the cosine of the angle between them. So if they're in the same direction, the angle is 0, cosine of 0 is 1. So this just becomes, well, I'm on this path B here, going this way, so it's E plus delta E times that length, which is just H. So this is E plus delta E times H. So we're doing, I'm going to use the term line integral. Laura, you have not had calculus?
I have.
You have had it. Okay. Line integral? It's iffy. Antiderivative?
That I know.
Okay, integral is just an antiderivative.
Right.
I think it comes down to historically, there's the debate, who started calculus, Leibniz or Newton? Newton primarily was working on derivatives, and Leibniz was doing antiderivatives or integrals. So basically I'm doing a line integral or a line antiderivative around this loop right here. So we did A was 0, along B, we just did that one, along C is 0, now we have this last bit. I'm heading back to where I started. So delta L along D is downwards. And so my electric field is going up, delta L is going down. What do you know about the dot product? If they're 180 degrees apart. Or what is the cosine of 180 degrees?
No, wait.
-1?
Yeah,
Wait.
negative. So this becomes minus E times H. So that's the left-hand side. The right-hand side, we have to deal with that little bit of fun right there. So negative 10. Actually, I'm going to go ahead and pop to the next screen. So E plus delta E times H minus E times H equals negative A delta B
did you have, just before, thank you. Oh, it's like the same thing. So that's essentially just work. Okay. Okay, I see. Okay.
You're good. We'll worry about the right-hand side of this one. So the left-hand side, let's simplify it. I'm just gonna distribute here. So I have EH plus H delta E minus EH equals negative A delta V over delta T. EH goes away. I'm left with H delta E equals negative A. A is the area. Well, my area is just H delta X. Because we're talking the physical area of this pretend rectangle. Times delta V over delta T. The H's go away, fortunately. Because the derivation should not depend upon some arbitrary value. And so now I'm left with this. I'm going to divide those sides by delta x, and so I get delta E over delta x equals negative delta V over delta T. Or for you calculus fans out there, we're taking the derivative of E and with respect to x, and we're taking the derivative of B with respect to T. So when I'm doing the derivative, when I'm taking the change in B with respect to x, I'm not worried about the T part. Well, if I've got my graph here, this is my electric field graph. What is the slope sheet? We did a graph of the slope. This is E with respect to x. What would the slope be? I'm looking for plus or minus sine or cosine.
It would be minus sine.
Yeah, it's negative sine. All right, so delta E over delta x. Well, first off, it's going to be negative sine, so negative.
Bless you.
What?
I sneezed,
Bless you.
sorry.
E sub m for max, sine kx minus omega t. And since we're taking the derivative with respect to x, the coefficient of x pops out front. So we get k out front. The change in B with respect to time. Well, again, cosine goes to sine, negative sine, so I get negative B sub m sine kx minus omega t. And what pops out front? As we do the derivative with respect to time.
The T?
See,
The T?
t does not pop out front now. Just like x did not pop out front here.
Right. Omega?
Close?
X.
Okay.
-1.
Combine the two answers there.
Omega T?
Negative
There we go, negative omega.
Right.
That negative is part of the coefficient. And so we get an omega here, and the two negatives cancel out. So what we have over there is that, let's just plug in, so delta E over delta X is, I have negative E K sine kx minus omega t equals negative from here bm omega sine kx minus omega t. And now the trig function goes poof. Actually, we've got a couple things here that will go poof. The plus sign, the negative signs will cancel out. The sign we can get rid of, and we, oh, that should be e sub m. And we are left with e sub mk equals b sub m omega. So we went through all of that to come up with this very simple 4-variable term, or 4-factor term, whatever it is. Something very simple. Remember, we're trying to derive the speed of an electromagnetic wave. From last time, what was the speed of a wave? What was the ratio?
Wait. It was T is 2 pi over omega. No wait, I'm looking here. 2
It's either going to be k over omega or omega over k.
omega over k.